Previously, we covered the core foundations. Now in part 3, we tackle Is Mars Actually Possible? The real story of getting humans there. Episode 3, Can we breathe, eat, and survive on Mars? Getting to Mars is only half the mission. Surviving there, that's the real exam. In the last episode, we covered the journey itself, the physics, the radiation, the months of deep space travel, with no easy way home. It's linked above if you missed it. Today, though, we move on. Because even if you land safely, you've arrived somewhere with an atmosphere you can't breathe, soil you can't eat from, and a sky that occasionally buries everything in dust for months at a time. This is episode 3 of Is Mars Actually Possible? And the question is straightforward. Can humans actually survive on the surface? Section 1. Breathing on Mars. The Martian atmosphere is roughly 95% carbon dioxide. It's also extraordinarily thin. Surface pressure sits below 1% of Earth's. You cannot breathe it. Full stop. Any crewed mission, then, needs to either carry its own oxygen or manufacture it on the surface. NASA has already tested one approach, the MOXIE experiment, Mars Oxygen. In situ resource utilization experiment, flew aboard the Perseverance rover and showed that extracting oxygen directly from Martian CO2 is physically possible. It uses solid oxide electrolysis, essentially splitting carbon dioxide into oxygen and carbon monoxide at very high temperatures. At peak performance, MOXIE produced oxygen in the range of a few grams per hour. As a proof of concept, that matters. As a life support system, it's nowhere close. A single astronaut at rest needs around 30 grams of oxygen per hour. A crew of 4, active and working on the surface, needs considerably more than that. Scaling this technology up to support a full crew for a full mission is an engineering challenge that hasn't been solved yet, not in hardware tested beyond demonstration level. MOXIE tells us the chemistry works on Mars. It doesn't tell us we're ready to depend on it. Section 2. Water and closed-loop life support. Water is the next hard constraint. Mars has water, locked in polar ice and subsurface deposits, but reaching it reliably, extracting it consistently, and doing so at crew scale is a substantial engineering problem. For now, mission designs carry their own water and recycle it as aggressively as possible. On the International Space Station, closed-loop systems recover somewhere between 90 and 93% of water from urine, sweat, and exhaled moisture. That recovery rate is genuinely impressive. But even so, a Mars crew needs a regular source to cover the losses that remain. More critically, those ISS systems are resupplied, maintained, and backed up from the ground. On Mars, a failure in the life support loop isn't a maintenance call. It's a crisis. Redundancy is the answer, and mission planners talk about it constantly. The problem is that redundancy has mass costs fuel, and fuel costs money and time. Every backup system is a design trade-off. There's no clean solution, just careful engineering and honest risk assessment. Section 3. Food, power, and dust. Food is a related but distinct challenge. Current estimates put a Mars surface mission anywhere between 18 months and several years, depending on the architecture. Carrying all that food from Earth isn't feasible. The mass budget simply doesn't allow it. NASA's Shapir program, Crew Health and Performance Exploration Analog, is running Earth-based simulations to study exactly this. Volunteers spend extended periods inside a Mars analog habitat, working through food production, resource management, psychological stress, and system failures under realistic isolation conditions. It's methodical, serious research, and it's generating real data on what holds up and what breaks down. Growing food on Mars runs into 2 immediate problems. The first is radiation. Surface levels are significantly higher than on Earth, which affects both crew health and crop viability in ways that are still being studied. The second is power. Cultivating plants under artificial lighting demands sustained, reliable energy. Solar is the most accessible option, but Mars receives roughly 43% of the solar energy Earth does. And that already reduced figure falls further whenever dust storms roll in and cover the planet for weeks or months at a stretch. Nuclear power, specifically small fission reactors, is increasingly discussed as the only option that gives a surface mission consistent, dust-independent energy. NASA's Kilopower project has demonstrated small reactor technology at a relevant scale. Demonstrated technology and flight-ready hardware, though, are not the same thing. Section 4. What this means for timelines. Oxygen generation, water recycling, food production, power supply. Each one is a hard dependency. You don't land on Mars and figure it out from there. Every one of these problems has to be solved, tested, and proven reliable before the first crew departs. That's not pessimism. That's just engineering. Publicly stated timelines from NASA and private partners keep shifting. Several targets from early 2026 reporting have already been revised. The underlying science isn't what's causing those slips. It's the integration of engineering systems. Getting individual components to function is a very different problem from getting them to function collectively, reliably, for years on another planet. Which raises the obvious question. When people say 2029 or 2031 or any other date, what does the science actually say about whether that's achievable? That's what we're getting into in Part 4. If this series is useful, subscribing is the best way to catch the next one. No obligation, but it does help. See you then. That is Part 3 of Is Mars Actually Possible? The real story of getting humans there. In Part 4, we explore the next key question. Subscribe so you do not miss it.